Whisker-based tactile perception is widely used in animals such as rodents. In nature, passive touch occurs as external stimuli deflect the loosely held follicle, enabling subtle contact and flow detection, while active whisking driven by muscle contractions supports environmental exploration and decision-making. Inspired by these biological functions, many robotic studies have developed whisker array sensors using capacitive, electrical contact resistance, triboelectric or vision-based tracking methods. These systems can measure contact and sometimes classify stimuli, but many designs are limited by either complex wiring for multi-direction sensing or passive-only operation without built-in actuation for exploration or manipulation. Our system draws inspiration from the Vibrissae of mammals, which incorporates 8 whiskers arranged in a circular configuration. Vision-based tracking serves as an artificial mechanoreceptive system, providing real-time monitoring of whisker rotations for accurate contact direction discrimination. Coupled with pulse-switchable permanent magnet (PSPM) actuation that mimics muscle-driven protraction, the system achieves both passive and active whisking. Here is the perception model and pipeline. We modeled each whisker as a rigid rod rotating about a central pivot on the membrane. Pixel displacements of the root markers were converted to real-world coordinates, using a fixed pixel-to-length scale factor. 2 experiments were conducted to quantify the ability to convert whisker movements into measurable outputs. The first experiment defined the mapping between pixel displacements and physical whisker movements. The second experiment defined the mapping between pixel displacements and externally applied forces. Both calibration experiments demonstrate good performance, showing a robust mapping between visual tracking and real-world contact signals. The actuation is achieved through the interaction between the iron composite and a pulse-switchable permanent magnet of each whisker. A forward pulse initiates attraction by activating the PSPM. Attracting the iron composite leads to rotation, while a smaller reverse pulse deactivates the PSPM and releases the whisker. Here is the force measurement results and payload experiment result. For the repeatability test, we let the whisker array underwent 1,000 activation-deactivation cycles. No progressive deformation or mechanical degradation was observed. To evaluate the whisker array's response to different airflow speeds, an airflow sensing experiment was conducted. Through comparison of the peaks and valleys of whisker displacement, different airflow speed can be classified. Also, using the fast Fourier transform, we can classify the signal from airflow and contact simultaneously. To assess the sensor's response to dynamic fluid environments, a servo-driven blade was used to generate periodic water flow at controlled frequencies. The results show that the whisker array functions effectively as a passive hydrodynamic flow sensor within a specific operational frequency band. As for viscosity sensing, our sensor can also characterize liquid viscosity without requiring additional robotic motion. By simply inserting the whisker array into a liquid, the sensor can actuate and sense viscosity variations over air, water, oil, maple syrup, and corn syrup by computing the pixel displacement decay during deactivation, eliminating the need for external force application. The object classification experiment was designed using 10 objects of varying shapes and sizes. Each data sample was obtained by placing the whisker sensor at 8 positions with respect to an object and recording the whisker pixel displacement values, and an accuracy of 98.7% was achieved. This experiment evaluated the sensor's ability to grasp lightweight objects using different numbers of whiskers. 3 configurations were tested, grasping with 8, 4, and 2 whiskers. For each object, the sensor performed 20 grasp attempts under 1 whisker configuration at a time. Grasping with the 8 whiskers achieved an average success rate of 90%. All grasping trials were performed without force control, and the objects remained undamaged throughout. This result highlights the whisker array's ability to handle delicate items without causing harm. To further demonstrate the sensor's affinity for grasping fragile objects, we conducted an experiment using delicate crystal clusters. Across 10 trials, the sensor consistently achieved successful grasps, fully securing the crystals. 3 comparative experiments were conducted. The first one is using Gelsite Mini as tactile feedback. It failed to detect contact in every instance. A second comparison was performed using 2 Finray soft fingers. Despite its compliance and ability to conform to object shape, the Finray gripper consistently compressed and fractured the delicate crystals in all 10 trials. A star-shaped Nunet gripper was tested. Despite its softness and adaptiveness, it achieved only 2 successful grasps out of 10, and in the remaining cases the crystals were partially destroyed. As a further proof of concept of robotic application, we performed a pick-and-place task with a live snail. The whisker array enabled gentle grasping and transfer from a water tank to a Petri dish. Snail moved actively in the Petri dish 30s after the placement, with tentacles extended, showing intact survival. This demonstration highlights the sensor's potential for safe robotic interaction with fragile biological organisms and points to future applications in biomedical handling and environmental exploration. Thank you for watching.